So with all that said, thank you so much for joining us. And with that, I'll hand it over to Penn for the presentation.
Hello everyone. Today we are going to explore how high-performance molded powder inductors are revolutionizing AI computing power. As we know, the demand for AI computing power is rapidly increasing and it requires innovative solutions to meet these needs. In this presentation, we will discuss the latest trends in AI power requirements, the advantages of molded metal powder inductors over traditional ferrite inductors, and how high-performance molded powder inductors are designed to address these challenges. Here, we see the growing power consumption trends in global data centers, especially those related to AI workloads. AI applications require significant energy for data processing, storage, and prediction tasks, which drives the need for more efficient power solutions to manage this increasing demand. This slide highlights the evolution of NVIDIA GPUs in terms of power requirements. As AI technology advances, GPU power demands have surged, driven by increasingly complex workloads and higher performance expectations. By understanding these trends, we can better appreciate the need for high-performance inductors that can support the growing power requirements of modern GPUs. The 800-volt high-voltage direct current architecture is presented as a future-ready power solution for AI data centers. This architecture improves power delivery efficiency from the grid to IT racks, reducing losses and supporting the high power density needs of next-generation AI infrastructure. From grid-level power delivery to chip-level power management, Eaton offers a comprehensive portfolio to support your needs, including supercapacitors, film capacitors, hybrid polymer capacitors, fuses, and more. Today, however, we will focus exclusively on one key component, the power inductor. Multiple factors drive the evolution of XPU power, from circuit topology to component design, and from passive to active components. Among these, the inductor stands out as a critical passive component that enables higher power density and improved efficiency. To address the stringent requirements of AI computing workloads, inductors must deliver high inductance density, operate reliably at elevated frequencies and currents, and ensure superior power density and efficiency. Additionally, they require low DC resistance and minimum EMI emissions, robust thermal management, and compact lightweight designs to integrate seamlessly into modern AI hardware. To achieve desired inductor performance for AI computing, core materials must provide high permeability and saturation flux density to withstand strong magnetic fields. They also require high thermal conductivity and resistivity to minimize losses and maintain stability across temperature variations, ensuring reliable performance in demanding environments. Compared to ferrite, powder cores have better preset temperature stability and softer saturation curve. This comparison shows how molded powder cores outperform ferrite cores in DC bias resistance across a range of temperatures. Powder cores maintain inductance better under DC current stress, which is crucial for stable performance in high current AI power applications. As AI computing platforms continue to push the boundaries of high current and thermal demands, selecting the right inductor supply is critical. Key considerations include experienced magnetic design and engineering team, strong manufacturing capabilities, high quality standards, strategic sourcing advantages. Based on the application, inductor, and magnetic material requirements discussed previously, molded metal powder inductors came into being. Molded metal powder inductors provide several advantages over assembly ferrite types: softer inductance drop under DC bias, over twice the saturation flux density, fully distributed gap, higher operating frequencies and temperatures, and lower resistance. These features translate to better efficiency, heat dissipation, and reduced EMI, supporting advanced AI power needs. Beyond single conductor molded metal powder inductors, the same material and manufacturing process have been applied to TLVR inductor evolution, resulting in molded powder TLVR inductor, naturally inheriting most of single conductor molded metal powder inductors' advantages. Beyond improving inductor and component performance, optimizing power distribution is essential. Vertical power delivery is employed to reduce resistance in high current paths. Specialized structures and optimized terminal designs are essential to ensure efficient current flow. The inductor's terminal configuration has shifted from all on the bottom to being on both the top and bottom. Here is a detailed table presents typical molded line couple 2-in-1 inductors, listing product dimensions, inductance values, and resistance. These specifications highlight the compact size and high performance of these inductors, suitable for integration into AI power modules requiring efficient power delivery. Typically, the coupling coefficient between the two phases range from 0.1 to 0.2, which is currently acceptable for most customer applications. These single-phase, two-phase, and four-phase inductors are designed for the same application but tailored for different requirements. Detailed specifications and layouts are provided. Inductance roll-off remains comparable across single, dual, and quad configurations, while temperature rise varies slightly due to reduced heat dissipation surface area in multi-phase designs. Some typical leading molded TLVR inductor size and ratings are shared in this table for your reference. As technology, products, and applications gradually mature, the product technology roadmap is as follows. This roadmap reflects the inductor industry's commitment to advancing inductor technology to support the evolving demands of AI computing power. In addition to AI computing high current power inductors, Eaton's extensive magnetic component product line also covers power to signal and components to device. In addition to magnetic components, Eaton Electronics can also provide circuit protection components, capacitors, terminal blocks, sensors, and timing devices to support your power management. In summary, Eaton's MFP and MTL molded metal power inductors are engineered to meet the increasing demands of AI computing. They offer superior current handling, reduced losses, excellent thermal and EMI performance, and compact designs, making them ideal for next-generation AI power solutions. For additional resources and support, please visit our web link below. Thanks.
Okay, thank you, Penn, for that great presentation. I see that we already have several interesting questions, but I want our audience to know that there's still time to submit questions if you like. Penn, are you ready to go?
Yes.
Good. First question, which core material has higher saturation flux density, ferrite or powder?
Powder core, due to the higher saturation flux density, for powder, it's about 2 times of the ferrite. Yeah.
Well, twice, okay. Next question, which core material has better temperature stability in terms of saturation flux density and magnetic loss?
Powder core too, yeah.
Yes.
Has a better temperature stability, yes.
Next question, which type of inductor has soft saturation characteristics? I'm not even sure what that means.
Molded powder core inductor, has soft saturation characteristics. Yeah.
Okay. Which type of inductor has lower EMI emissions?
Multi-powder inductor too, okay, due to the fully distributed gap, along the magnetic path. Yeah.
Yeah. But it's interesting. So many sessions today has been related to AI computing, because there was one earlier about capacitors, and you would imagine even everyone's doing high voltages. So it's interesting that it's touching all these areas here. Let's see. It looks like we've had most of the questions answered pretty quickly here. So before we wrap up, is any key takeaways you want to give our audience today, Ben?
I think today, it's an AI, era here. Okay, so in order to support the AI computing power, the power inductor is basically playing the key role here.
Yeah.
To help to boost it. So that we basically help can boost the AI computing power, by increasing the power density and performance, for the power inductor.
Yeah, it makes a big difference. Yeah. Okay, well, Penn, thank you so much for this great presentation, and thanks for sticking around for the Q&A. Before we close out this All About Analog and Power live session, I'd like to announce our prize winners for this session. So congratulations to Paul Pistori and Catherine Stroh. We'll be in touch with you in the next week to make sure you have all the information that we need to send these All About Circuits goodies. Just a moment from now, you're going to be redirected to Eaton's Summit Series microsite. So I encourage all of you to check out other live sessions, keynotes, and published content for our month-long annual event. So Penn, thank you again. And I want to thank our audience for joining us for All About Circuits.